So let's look at our vector equilibrium here. And there's one piece that I really want to pull out of that first video we watched, where the welder was pointing out that the vector equilibrium consists of 4 hexagons, excuse me, symmetrically arrayed in 4 planes. And that's what's represented on the screen here, where you can see the hexagons in different colors, right? Hexagons being 6-sided shapes. And you've got the red one around the center, you got the blue one, that's the outline, and then you've got purple and green at these angles. And what's so interesting about this is that these symmetrical planes, this is a 4-dimensional shape. And it totally blows out of the water our accepted familiar XYZ axis 3-dimensional coordinate system, right? And so the 60-degree coordinate system of the vector equilibrium stands in stark contrast to the Cartesian 90-degree system given by our familiar cubical XYZ axis, right? Cartesian meaning from Descartes, who was he had a very mechanical view of the universe. He envisioned the cosmos as a big clock, and everything was strictly physical relationships, form pushing on form with force. And he was missing a lot of the subtlety of what we now know is real, and missing what is on this level like very obvious, that there are actually 4 dimensions of space. There are these 4 symmetrical planes that intersect at one point and can theoretically radiate out infinitely without ever crossing again. But this is actually a very key difference in these two systems, where the Cartesian model suggests it's got these 3 lines, right? X, Y, and Z that theoretically go infinitely out in one direction, right? That Z-axis is going to go as far that way as you can ever go and never come back and never loop back around. Whereas the vector equilibrium is self-contained. It's self-reflected. It's a coherent system unto itself. And this to me seems like a much more accurate way of representing the way nature actually works, right? In natural systems, there are no outputs which are not also inputs for other components of the system. Think of the way a healthy forest composts and generates soil, and there's this flow of resources. Whereas it's only in the human mind, I think, that there's this idea that there's an infinite line expanding out into some theoretical space and time, so that on some level it justifies, cool, like, well, I'm just going to leave a pile of garbage right here because I'm going this way and never coming back, right? And this is just going to go infinitely out. This line of progress and expansion and profit, goes infinitely on this upward trajectory. And so I can just leave whatever behind me and it's fine. That's not how it actually works. And so the vector equilibrium encodes that, as opposed to the Cartesian system, which doesn't, and encourages us to think in these 90-degree structures as opposed to 60-degree structures, which gives us a very different idea of how reality works. So this cube octahedron, the vector equilibrium, has taken us from 3D reality into 4D space. And Fuller himself says synergetics permits conceptual modeling of the 4th and 5th arithmetic powers. That is, 4th and 5th dimensional aggregations of points or spheres in an entirely rational coordinate system that is congruent with all the experimentally harvested data of astrophysics and molecular physics. So what he's saying is like, look, like synergetics, this vector equilibrium model, gives us 4th and 5th dimensional a 4th and 5th dimensional coordinate system that is completely congruent with everything we already know about astrophysics and molecular physics. That seems pretty cool. That seems exciting. And so if we're going to talk about 4th and 5th dimensional space, I think it's worth it to review some of the definitions of the word dimension. So there are a few distinct meanings, falling into basically three categories. One is the physical extent or measurement, like what are the dimensions of this room? Oh, it's 12 feet by 20, whatever it is, right? We can also talk about orders of complexity in the most general senses, and like the many dimensions of an issue or a problem. This is how it's most commonly used, and this is sort of how we can use it colloquially in multidimensional medicine, where it's like, oh, I have many dimensions. I have an emotional self and an intellectual self and a physical self and a spiritual self, and many different dimensions to who I am. That's sort of the colloquial usage. And then third, we have the specifically mathematical application in terms of the number of independent terms required to identify a point in space. And so our conventional system uses three independent, mutually perpendicular axes in space to accomplish a task, right? So we use X, Y, and Z, and we can identify a coordinate in space by giving its XYZ axis, right? Boom, there's where the dot is. And this geometrical understanding is usually the first meaning that occurs to people. You commonly say space is three-dimensional, right? It's sort of assumed in public discourse, common understanding, space is three-dimensional. However, believe it or not, this seemed unacceptably limiting to Fuller. And he is saying how exposure to the ordered polyhedra of mathematics, what we've been talking about here, and also to organic structures like crystals, this makes an orientation towards perpendicularity seem quite arbitrary. You know, the choice of the cubical structures is arbitrary. Right angles are sprinkled throughout geometric shapes in nature, but they're by no means dominant. And more often than one might expect, 90-degree coordinates provide an awkward framework with which to describe both naturally occurring and conceptual formations. It's not always or even often the most efficient or accurate way to define space. Fuller viewed the Cartesian coordinate system as a remnant of flat Earth thinking. Early man, finding himself on a huge flat expanse, assumed that up and down and back and forth were the fundamental directions of the universe. 90 degrees was the obvious natural angle with which to segment and measure space. So humankind has had more and more evidence of nature's radial and spherical bias throughout history, from the discovery of the shape of planets to the behavior of radiation and cellular growth. But neither Copernicus's spherical Earth nor the vast array of biological and physical phenomena, all suggesting that angles other than 90 degrees would provide more natural or convenient measurement systems, have succeeded in reorienting the perpendicular bias of mathematics. So that's part of what we're doing here. It's like, hey, 90 degrees is not the only way to do it, not even necessarily the best way to do it. So it's become part of convention, and that space cannot accommodate a fourth perpendicular direction is just one of the intrinsic constraints on this arbitrary choice of system. And yet too often this limitation is seen as the only characteristic of space, right? We're locked into three-dimensional thinking. We think these are the only characteristics possible, and so we assume the limitations inherent in that system. And so once we break this open and see that that this vector equilibrium is actually the defining structure of space, and that all the other geometric Platonic solids that we've talked about arise and are encoded within it, all of a sudden we're broken open into a more multi-dimensional worldview. Okay. So the Cartesian coordinates require three coordinates to identify a point in space. This is also possible in the more spherical system. So really what we're looking at here is, okay, this is just the geometric explanation of the jitterbug, that structure he was playing with. Here's that toy that he was playing with, and here's just the drawing of how he was manipulating it. So we don't need to spend a lot of time here, but you can study this image just to see how the shapes change and it twists and transforms. And he called it the jitterbug because it's sort of with pulsative asymmetry, as vibrations are flowing through, different vector forces are influencing it. It's sort of jittering. And I think of the way we saw the cymatic structures. So there's vibrations flowing and the whole structure is sort of just like jittering a little bit, but it's bouncing in between these really harmonic, beautiful structures. Okay, so that's that. But really what we're talking about here is the difference between a Cartesian coordinate system, with which we're all familiar and which was, for me, so frustrating and confusing all through high school, with a spherical coordinate system, which is what the vector equilibrium is based in. And so that spherical approach is much more suited to Fuller's radial understanding of the universe, which the spherical coordinate system is really, and Fuller's approach to it is converging and diverging, right? There's this sense of things collapsing and exploding. And these are the two primary directions, and everything else organizes according to that. Like the way he was playing with that toy, all he was doing was converging and diverging. And everything else spun around and created shapes relative to that coming together and coming apart, collapsing and exploding. So on some level, we can say that there really are only two directions in the spherical coordinate system. So that brings us to the end of section 7. In section 8, we're going to get deeper into the spherical realm and see how spherical dynamics actually work. And there was a little hint in that Nassim video of the toroidal structure. And so that's where we're going next. But let's pause first for questions, comments, confusion, enthusiasm. It's a lot. There's a lot of, that's a very technical section, isn't it? There's a lot of math and geometry in that, but this is the geometry of thinking, right? I think that's the subtitle to Synergetics is Bucky's book, Synergetics, the geometry of thinking, geometry of consciousness. So yeah, any thoughts, comments, questions? Sam.
I don't exactly understand like how we've transferred from the nested polyhedrons to like using a vector to find the octahedron. Like what is the vector's part to play?
Yeah, we definitely I skipped over some of the more technical stuff in that transition, because basically how we got there is if we start replacing the edges of our polyhedra with vectors, right? So like here, if you have a tetrahedron but all of these edges are vectors, you heard him say it's quadrivalent, right? It's quadruple bonded at each edge, right? So there's vector going this way and this way on each side. So it's all tightly wound. And so once you start introducing the vectors into the equation as opposed to just edges, the natural outgrowth, the sort of unavoidable conclusion of that experiment, you end up with the vector equilibrium. And so there's a whole bunch of really interesting and playful distortions of Platonic solids, and there's Archimedean solids, and you start truncating, and there's a whole bunch of procedures and interesting things that you can do in between. But the sort of inevitable conclusion is that vector equilibrium. So we skipped over a little bit of stuff, but we got straight to it there. Yeah.
Would it be accurate at all to say a vector would be like an input of energy or movement?
Yeah.
Energy, maybe?
Yeah, absolutely. The vector is a measurement of direction and magnitude of energy. Okay. So, if I push my chapstick across the table, I've increased its vector in that direction. Whereas as it's going, the friction between it and the table is a vector in the opposite direction. But by pushing it, the vector line in that direction is greater than the vector line in this direction, therefore it moves, right? So yeah, the vector is the simplification of the most simplified possible representation of a force or movement or energy. Yes. Clear?
Yeah.
Más o menos?
It's a really complex concept.
Yeah. Yeah. It's a lot to wrap your head around. And so one of the things that I recommend is drawing. One of the ways that has helped me to conceptualize this more accurately than anything is simply to have a straight edge and a compass and a piece of paper and start playing and just start drawing circles and then start connecting dots and see what arises, see what patterns come to mind, coloring them in pleasing ways, or just playing with like, oh, I'm going to color in these symmetrical parts, and the color exposes. And when I first started doing that practice, there was this like explosion, like my dreams got way more intense for like the month after that, and I could feel that it was actually changing the way that my brain and heart were able to perceive reality. And so drawing is a really good thing. And then the next level of that is drawing shapes and cutting them out, and playing with like cardboard and gluing them together. And like Bucky was a big fan of using ping pong balls or little like foam balls with toothpicks in between. And so using those toys, you can reveal a lot of how all this works. Also, a tensegrity toy is a fun thing to have as well, because then you can see, and like, depending on how you look at this, if I structure this just the right way, like, okay, there's a very clear Star of David in front of me right now, and you can see there's a cube encoded into this as well. Let's see if I can do it for the camera, right? So you can like, it takes some brain warping, but it's just, it's like a mandala. You stare at it long enough and all of a sudden it's sucking you in. Yeah. So there's I'm giving you a big brain dump here, and that's part of the digestive process, is to play with it and work with it. And what I like about drawing is it's an embodied process. It actually gives you a somatic point of integration to bring the shapes and these understandings through your physical body. Yeah. Okay. Any other comments on that? Feeling good? Sam, go ahead. Keep us going.
How were those shapes like burned into that rock?
How were those shapes burned into that rock? That
has it been like verified that that's like ancient?
I believe so. Yeah. I mean, it's one of the most ancient sites in Egypt, and I don't know how they did that, except that they definitely had technology that we don't know that they had, and that we probably don't know about. There's a bunch of stuff, carved on the inside of all those pyramids that's like, cool, like that's a big light bulb. And one of the cool things that I've learned about the pyramids is that the Nile River used to run like right in front of them, right? Over the millennia, it's migrated. And the way the pyramids are built is there's alternating quartz and limestone, right? It's a conductive substance and an insulating substance. And stacking conductive substances and insulating substances on top of each other, and then having water move in and out, creating suction, that's the recipe for a battery. So there's some sense that the pyramids were actually big power plants. And so there's a bunch of cool stuff going on there that we don't know about. So how did they burn it? I think they probably did some Doctor Strange sort of magic on it.
I'm gonna go with aliens.
Oh yeah.
So it's like a laser magic.
Even if it wasn't aliens,
well, we're the aliens.
It was aliens. Yeah.
We forgot we're aliens.
Yeah, we forgot that we are the aliens. Right. No, I wonder if it was a sonic device of some sort that we're using sound to, because again, it's sound vibration that gives rise to all these structures. And so if you had a sonic device of some sort, you could imprint it really quickly. So that's my speculation, but it's a great question.
It's insane.
It's
super cool.
Yeah, pretty wild, huh? Yeah, cool. Okay, let's move right along here.